In the next section, we'll look at Cartesian trees, which is a different way to look at the range mean query problem. It seems first not to have to do much with sparse tables and these other solutions, but we'll bring it back together in the subsequent section. Let's look at this problem again and try not to focus too much on how we store it, how we solve it first. On this slide, I want to draw this more graphically. So each element in the array is shown as a bar. It's a little inconvenient to talk about the minimum bar because I want to have this metaphor that something sinks down from the top until it hits the first column. So let's in this part look at range maximum queries. It's of course the same problem. You can just take your array and negate all numbers or invert the comparisons. It doesn't change the problem at all. It's just to make the pictures a bit more, to make the metaphor work out better. So range max in this section, okay? Whenever I will probably say range min a few times and mean range max, so you have to be aware of that. It's range min query all over the literature, which is maybe inconvenient. As I said, drawing it is usually nicer with max. Conveniently, the abbreviation is the same, so maybe I should just say RMQ and you have to substitute the right thing. Good. So same problem. RMQ in this section means I want to find the maximum in the range. We'll keep the same conventions. We're interested in the position, not the value, and the leftmost of the positions where the maximum occurs. So here's another example, just for the metaphor. You have a range, and so you can imagine you take that range, you take a wooden bar, a plank of that width, and it sinks down until it comes to the rest on the highest of these poles. And so the position where it touches the first pole, that's the range max, right? And the task stays the same. We want to pre-process an array that's given and do faster at query time. Right, so this is something, because we have the time this year. Let's put in a little question about trees. Okay, this is not something autocorrection lets you go through. Okay, I started a question. Maybe let me add an option for that. Would anyone like to click? I've heard the term somewhere but don't remember exactly. In case you want that third option, it's now available. It's one of these things we don't need trees. It's not anything that we'll build on. It's just in case a lot of people knew it, I would have adjusted the explanation. It seems that no one has ever heard of them. In case you're curious, the word might suggest it's a mixture, it's a chimera of trees and heaps. So it's a binary search tree that is at the same time a heap ordered tree, but according to different parts. So each key has a value and a priority. It turns out to be the same concept as Cartesian trees if you look at it from the right perspective. But if you haven't seen trees at all, that doesn't help you much. And as I said, it's not needed for this. So let me just explain what a Cartesian tree is then. We construct a binary tree in the following way. We let a line for the entire range sink down from the top. It will make first contact on the range max of the entire range, so the overall maximum of the array, the leftmost occurrence of those in case there are several. In this case, that's here at position 18. Then we create a node which will become the root of a binary tree. After that, we continue this process independently on the left and on the right of this maximum. So on the left, we'll sink down a pole that's only as wide as up to this point. So that will find the next largest element. Well, the next smallest is right, but is the largest among the ones on the left. So in this case, this position 9. And that will be the left child of the root. Connected. On the right, there's just a single element, but then this is also the maximum, so that becomes the right child of the root. And you continue like this recursively. So after we've done this, we take a piece of timber and let it sink down. That is just below the two things already in the tree. So that will hit ground here. So this becomes the right child of the left child of the root. And we do the same on the left as well. Is the construction clear? So you take the nodes that you already have in the tree, they will leave gaps, and you let little wooden poles sink down in the gaps until they touch a pole, and then that becomes the child of the lowest node. And so you keep going like this. Every node you create might have two further children. Sometimes there's only one child because it's the outermost in its range. And eventually you reach single element arrays in the recursion, and then you just stop with a leaf node in the tree. All right? So again, find the maximum, put a node there, recurse on the two sides, continue with the same construction. That gives you the Cartesian tree. And the Cartesian tree is quite nice because it allows you to find range maxima. If you want to find the maximum in a range, you go to the nodes that are outermost in that range. So more formally, you take an in-order traversal of the tree, where you visit first everything on the left, then the root, and then the right to the right subtree, and you assign indices to the nodes when you visit them. Another way to say it is if you draw a node always vertically above its position in the array, you immediately get that this is the left to right ordering, right? You see the nodes are just 0, 1, 2, 3, 4, if I go sweeping from left to right. If you've done that, you can go to the nodes of label 6, 6, and 14, if that is the range you're interested in, and you find their lowest common ancestor, and that has to be the range max. All right? So again, finding the range maximum in a range means take the two outermost nodes, vertices in the tree, and find their lowest common ancestor. Next step is if we have this tree, we don't need the array anymore. We can do the same without looking at the array at all. In fact, all I needed was the in-order index of nodes. And I can assign these just knowing the tree. I don't need to draw the tree in any way, or I don't need to access the array to do that. I just do this recursive procedure, visit the root. Start at the root, visit the left subtree, then visit the root and assign it its number, and then go to the right subtree. So if you do this recursively, you would start labeling this one with 0, then you come back from the left subtree, assign this, then label 1. That's in-order traversal, and you assign indices as you visit nodes. You can do this without the array, just the tree. So you can assign nodes these indices, so you can find the nodes that have the indices delimiting your range, and you can find the lowest common ancestor and return its label. You don't need the array for that. Because I don't have the array, I should really draw my tree like you would normally for a binary tree. This still reflected the relative heights, but this is it's just my way of drawing it, right? So this is really what's given in the tree. So same thing, just now any connection to the array is lost. But we don't need that. Let's see if you got this part. Here's a little example of a Cartesian tree and an array. Remember, we start at 0, right? This leftmost thing should have index 0. I just tried to convince you that the tree is everything you need to answer range max queries. There you go. Answer the range max query on the slide and see if that works out. And while you're working, I'll just draw some helpful lines. So that you're not lost in the counting at least. It's a lovely variety of answers. But yeah, it looks promising. Okay, we have 25. That was roughly about everyone, I think. Let's briefly see this. There's a cluster for 3, which is good. A cluster for certain smileys, which is also good. So let's briefly do this. The range we were interested in is 1 to 5. So the first thing to know is that this is including the endpoints. The cool thing about this one is I don't even have to tell you numbers in the array. So there's no way to figure this out because I haven't really pinned down any specific array. What we'll do is we'll trace the 1 up to its node and the 5. That gives us the range. And then we find the lowest common ancestor of those two guys. So we walk up until they meet. And then we follow down again to get the answer. So 3 is the right answer. That's where the maximum in this array must be if this is the Cartesian tree for it. And here's a concrete example that I generated this from. But again, you don't need this. And so, yeah, there you get the 3. So Cartesian trees look like they're really interesting because they take the essence of the problem and do away with the unnecessary detail. If you give me an array, you can always find a different array that has the same answers for all range max queries, or all range min queries for that matter. But the arrays are different. They have different values. Right? And even if you say, we've done a similar trick in sorting, we said, oh, the values don't really matter, so I can as well assume that the things I sort are just the numbers 1 up to n. I could do the same for range min queries, but then still 2 different arrays that are permutations of the numbers 1 up to n, they could still have the same answers to all range min queries without being the same permutation. So in a sense, the problem is more lossy. It ignores more information than sorting. And the Cartesian trees seem to be a slick way to get exactly at the amount of information contained in these queries. They preserve all the range min queries, and as we'll see, actually nothing else. Here's a bigger example. You'll probably have to zoom in to see it properly. So that's if you draw the array and then poles of the appropriate heights. And that's how you would normally draw a tree where the depth in the tree is the y coordinate. And you can do away with this scaffolding. So you get the tree like this, and you can still answer all the arrangement queries. All right. So why do we care about these arrangement queries? We already know a slick way to get fast answers for range max or range min using the sparse tables. The only problem was that the space wasn't optimal. But now I told you, oh, instead of looking at this easy range min query problem, let's look at lowest common ancestors in trees. But isn't that where we started? We started with the suffix array or suffix trees. We started with suffix trees, and we wanted to find the lowest common ancestor of 2 leaves. And after a long and winded road, I told you, the solution is to look at the lowest common ancestor of 2 nodes in a binary tree. So why all this journey? This problem doesn't look any more fundamental or easier to solve than finding the lowest common ancestor of 2 leaves in a suffix tree. And in a way, it isn't. We'll use it for something else. I made this comment before. If I give you the Cartesian tree, all the answers to all possible arrangement queries are determined. All the information needed for that is contained in this tree. And I left out the labels of the nodes on purpose because they're all implicit. If you know this is the root and has left and right child and so on, that's all you need. Okay? So we can count how many different inputs are there for arrangement query problem of a certain length. So if I tell you the array has length n, then how many possible answers are there for all those arrangement queries? There's a quadratic number of them, and every output is an index. So a naive bound would be something like n squared times n different answers. That would be quadratic. But, sorry, that's bogus. You would have to take n different outcomes and raise that to the power of the number of them. So naive, not in blue. A trivial bound would be something like n to the n squared, which is an absurd number. It's really big. So if you would take the space of that, you would take the log, but then it would still be n squared log n as the space bound, and we've already seen how to beat that, right, very easily. We've seen a solution that uses n log n space. But there's a catch. The sparse table solution still needs access to the array. Remember, if we answer queries, we need to look at the array to decide which of if the blue or if the green region gives the minimum. What we use the Cartesian trees for is to count the different numbers of RMQ instances on a cleaner object, namely binary trees. And one way to do it is to just look it up. The Catalan numbers counts exactly the number of binary trees on n nodes, and it can be written as this. There's many interesting combinatorial proofs, but we're not a combinatorics class, so I'll spare you. There's an easy way to show an upper bound by encoding the tree in a unique way. So this is if you want, it's a compression method. We're given a binary tree, we produce a sequence of bits, and from that sequence of bits you can decode the tree again. So let's see how we can do this. There are different ways, but I'll show you a particularly simple one. You visit all nodes in pre-order. Pre-order means I start at the root and I first visit the root. I'll tell you in a second what visit means. We'll do something. After you've dealt with the root, you go to the left subtree and recurse there. And once you come back from the left subtree, you go to the right subtree and do the same. Okay, that's pre-order. The important part is that you do the root first. And when you visit a node, you store 2 bits. Namely, whether or not it has a left child and whether or not it has a right child. Okay. So again, you visit all the nodes in pre-order. Whenever you visit a node, you output 2 bits. You append 2 bits to the encoded string. Let me briefly peek. Yeah, we'll practice that on the next slide. And maybe we'll do the decoding just on the next slide. So for now, I want to bring this point first. So by counting the number of trees, we can count the number of equivalence classes of arrays if you only care about RMQ. And we'll see how to exploit that in the next section. I don't want to practice this encoding a bit because I think it's kind of neat and useful to see that this really works. So again, remember, we go in pre-order through the tree and emit 2 bits when we visit a node, whether or not it has a left or right child. So let's do this on this smaller example, just to practice that before we use it. So it's 4 nodes, 2 bits each. I'm expecting answers with 8 bits, right? Do you want me to show the last slide with the code? Well, by the magic of digital, let's just copy it. Okay, I want to finish on time, so I'll start showing the example. You can still vote if you want. Let's first figure out in which order we visit the nodes. We start at the root and we first visit. So this is the first one that we look at. And then we go left first. Go to the left. We visit the root first, so that becomes number 2. Then we go to the left subtree. We visit the root. Now we go to this guy's left subtree, but there's nothing. We go to this guy's right subtree, which is also nothing. Then we're done with this node, so we return. We've done all the left subtree of this guy. So we go to the right subtree, but there's nothing. So we're done. Go back up, and well, there was only one node left, I guess. So that's the order in which we visit the nodes. And once we figured that out, the rest is just writing down whether or not they have a child of the appropriate direction. 1 has 2 children, so it must be 1, 1. 2 has just left, so it's 1, 0. And 3 and 4 are leaves, so they are both 0, 0. All right? I think I've seen that a few times. There's a few other suggestions too. How did you get these vertical bars? Like this one. Can you send line breaks? Or is this just, yeah. And you guys coordinated on the same emojis even. Whose birthday is it? Yeah, I think that's a good point to leave it. I do want to show how to decode the tree, but I'm a bit out of time. Let me just show it on this example very rapidly. So let's pretend we don't see the tree. Okay, I just see this bit string, and I'll start drawing. Oh, you can't see. Thanks. I zoomed in so I don't see the tree. I pretend I've forgotten it. We start with the first 2 bits. So we know this is from the root. So we have to draw a node with 2 child ports, 2 slots for children. And now we do a pre-order traversal. So we know we always go from the leftmost onwards. So this is the first slot that we look at. And now we pick the next node, which is one of this type. So I add a node. It has a left child, but it has no right child. So I can add this little box just to indicate this is a null pointer. There's nothing missing here. Then again, even if I forgot where I was, I can always take the leftmost free slot. And now I have to put a new node here. And it's of a 0, 0 type, so it doesn't have any children. It's a leaf. Then I'm done with this part. And the next node, I walk along the tree until I find the first missing node slot. And so here I go, it's the only one left. And as a sanity check at the end, I should have a complete tree with no dangling child slots left when I'm done reading the bit string. All right? So that's how you decode. And so that should convince you that it's an encoding for the tree. You can encode it and you can get the tree back. Why this all makes sense, why have we talked about trees so much and counted them, that you will see on Thursday.